Hello students, in this video series we are seeing about IPv6 addressing. In the last two videos we have seen what is the motivation behind IPv6 address, what are the advantages, then how IPv6 address differs from IPv4 address. And in this video we are going to see about the address space allocation in IPv6. Like in the case of IPv4, IPv6 also has the address space, and the address space we have divided into many blocks, and each block is used for a very specific purpose. Some of the most important blocks are special addresses, global unicast, unique local unicast, link local address, and multicast addresses. In that, the global unicast, unique local unicast, and linked local addresses are used for host to host communication. That is, one host is communicating with the another specific host in the internet. All these three are used for this host to host communication. Whereas the last one, multicast address, is used for delivering the packet to a group of nodes. Let's see the global unicast address. So basically, as I told, it is used for one-to-one communication. In other words, we'll be calling it as a host-to-host communication. Always the block prefix is 001. So we know, can you please recall what is the IP length, IPv6 length? So it is 128 bits. In that 128 bits, first 3 bits, okay, first 3 bits is by default 001 when you are using the global unicast address. The remaining number 125, so we are using 2 power 125 addresses are there. The total size of the block is 2 power 125. So we just think what is the scale of 2 power 125, how many interfaces we can identify by using IPv6 address. If you are taking the entire IPv4, it is 2 power 32. But here, if you are taking the unicast address alone, the total block size is 2 power 125. So that much increase in scale we have achieved in IPv6. Okay, let's take this 128-bit address. So here we are going to see the divisions in global unicast address. So the global unicast address in any IPv6 address, it is 128 bits. So this is the total length, 128 bits. So just divide this into two categories. So here 64 bits, on this side 64 bits. So you know, an IPv6 we are using the network ID and host ID. We'll be dividing the addresses into network and host ID like this. Here first broadly divide this into two divisions, 64 bit, 64 bit. The second category is called as the interface identifier. So the second 64 bit is called as interface identifier, which is similar to host ID in IPv4. The first 64 bit, so again we are dividing into two, that is the first 48 bit is called as a global unicast prefix. It's called as a global unicast prefix. The second division, you have to see in length, the global unicast prefix is 48 bits. The second division is called subnet identifier. Subnet identifier is 16 bits. So 48 plus 16, 64 bits. Like this, you remember, we are dividing into two categories. One is similar to network ID, another one is similar to host ID. But in IPv6 terminology, the host ID should be called as the interface identifier. And the first 64 bits is again further divided into two divisions: global unicast prefix and subnet identifier, which is respectively 48 bits and 16 bits. So what is the use of this global unicast prefix? Let's see with the diagram. So this is your organization. You take any private organization where thousands of systems are there in this organization, which is connected to internet. It's a very big organization where you are having a lot of sub networks. For example, I am drawing three sub networks because in the large organization, each department will be having the separate sub networks and separate network policies for the sub network. To identify this organization, technically it is called as a site. To identify this site, global unicast prefix will be used. By based on this 48-bit number, the site location will be identified. That is, your organization will be identified. Then in this site, to which subnetwork the data should be delivered. Okay. For that, we will be using the subnet identifier. So totally, how many subnetworks you can define? 2 power 16, which is roughly equivalent to 65,000. So 65,000 subnetworks you can define within an organization. Okay, so this is a very huge number. And how many sites we can identify in the internet? Okay, so the site is identified by the number global unicast prefix, which is 48-bit length. But in this 48-bit length, the first three bits are reserved 001. So you take the remaining 45. So it is 2 power 45 sites. 2 power 45 sites, ISPs, organizations can be identified, and within each organization, within each site, 2 power 16 subnetworks can be identified. Then you know the following logic: within each subnetwork, how many hosts can be identified? That is 64 bits. So within this each subnetwork, okay. So these are the host. Host means referring the computers. So like that, how many hosts can be connected? It is 2 power 64 host or interfaces can be used. Yeah, is it clear? Now coming to interface identifier. In interface identifier, it is 64-bit. So you know, in IPv4, the host ID will be decided by the DHCP server, or the router will be assigning the host ID. But in the case of IPv6, auto configuration is supporting the interface identifier. So let's see. Um, Hope you know about physical address or Ethernet address. Do you know the length of address? Physical address is 48-bit length. So in IPv4, there is no direct relationship between um, logical address, 32-bit IP address and the 48-bit physical address. But in IPv6 there is a relation. So here Ethernet address 48-bit. Okay. Another words we are calling it as a physical address or MAC address. So this 48-bit we are dividing into 8-bit section. So totally we are having 6 divisions. Divided into 6 divisions, each of 8-bit length, the physical address. So if you want to derive the interface identifier, the host ID from the existing Ethernet addresses, concentrate on the first byte. Okay, concentrate on the first 8-bit. Okay, always the 7th bit will be 0. Okay, we have to change this to 1. 0 to 1 we have to change. Then after changing this, after 24 bits, the original total length is 48 bit. What is the first thing we are doing? We are converting the 7th bit from 0 to 1. Then after 24 bits, we have to add 15 number of ones. 15 number of ones. Then the 16 bit is 0. This is what we are adding. Okay. In all the interfaces we have to add this 15 number of ones. In the 16th bit is 0. So the original bit is 48 plus how many bits we are adding? 16 bits we are adding. Okay. So 15 plus 1. 15 ones and 1 0. So totally it becomes 64 bit. So what is the base for this 16 bit? What is the base for this 64 bit? It is derived from the existing physical address. From the existing MAC address, we are deriving the interface identifier. Okay. So this is one way of auto configuration. Through Ethernet address, through MAC address, we can derive the interface identifier. In other cases, we are having the EUI number. The expansion of EUI is extended unique identifier. Extended unique identifier, so which is an IEEE specification. So there is an IEEE specification. So basically this EUI number is 64 bits in length. 64 bits. The original MAC address, physical address is 48 bit. Then we are stretching it to 64 bit by adding 16 extra more bits. But EUI is by default it is 64 bit. Okay, it is another physical address equivalent to the Ethernet address. Here we are doing only one change. The 7th bit, as I told earlier, is by default 0. We are changing it to 1. Then this new number becomes the interface identifier. By using these two ways, we can derive the interface identifier for a system. Let's see with the problem. Okay. Now they have given an for a specific system. They have given the EUI number. Okay. The EUI number is 64 bit. Okay. but normally we are using the hexadecimal notation. The hexadecimal number they have given is F4, B7, 17, FF, 17, 21, 37, D2. So it is a hexadecimal base. So this number they have given. In two ways we can derive the interface identifier. One from EUI number, extended unique identifier. The another one is by the from the physical address. So in the problem clearly they have mentioned, they have given the EUI number. They are asking what is the interface identifier. What is the interface identifier? It's easy. So what is the only one change we are doing? We have to change the seventh bit. Always the seventh bit will be 0. We got to change it to 1. Where to find the seventh bit? We know a hexadecimal number will be taking 4 bits. So this F will be taking 4 bits. This 4 will be taking 4 bits. This B will be taking 4 bits. If you are counting the values, so totally up to 64 D2 64 bits will be, you can check it. F 4 bits, this 4 bits, B 4 bits, 7 4 bits. If you are adding together, it will be 64 bit. Our target is we got to convert the seventh bit from 0 to 1. So 4 bits, here another 4 bits. So seventh bit lies here. The seventh bit lies in the 4. So what is the binary number of 4? The binary number of 4 is 0, 1, 0, 0. Okay. The binary number of 4 is 0, 1, 0, 0. So here this 0 will be the fourth bit. This 1 will be the fifth bit. Sorry, this 0 will be the fifth bit because already 4 bits we have taken for F. So this 0 is the fifth bit, 1 is 6, seventh bit is 0. Okay. So we got to change it to 1. So the new number will be seventh bit we are changing to 1. Okay. Then what is the decimal number of this 0110? It is 6. Let's check it. So now this 4 should be changed to 6. But how to write it? When we are representing the hexadecimal number for the IPv6 address, we are having 8 sections and each section will be taking 4 hexadecimal numbers. Here the EUI number, only 2 hexadecimal numbers are there, but from this EUI number we are deriving the interface identifier which is part of the IPv6. So we have to club it together. We got to combine 4 bits as a section. So this you can note, we got changed 4 to 6 by changing the seventh bit. I'll be writing the new identifier, interface identifier. So this will be F6 and combine these 2 bits, these 2 hexadecimal numbers, colon 17FF, another section, then 1721, another section, 37D2. Now totally this will be 64-bit interface identifier. So this is how we are deriving the interface identifier from the EUI number. The another method is if they have given the Ethernet address. Ethernet address is only 48 bit. From this 48 bit, how we can derive the interface identifier? For this, we can see a problem. Let's take the same number. Uh, they have given F4, E7, 17, FF, 17, 21. It's a hexadecimal number they have given. But now they have given the physical address. The physical address, as I told, the length will be 48 bits. So this F will be taking 4 bits, this 4 will be taking 4 bits, as we seen in the last problem. Now here also the first step is same. Convert the 7th bit from 0 to 1 we got to change. Where the 7th bit will be there? So it will be in this 4. Okay, what is the binary number of 4? 0 1 0 0. This will be the 7th bit if I are changing 0 1 1 0. The same logic as we seen in the last problem. So 4 becomes 6. And what is the second step we have seen in Ethernet? We have to add 16 more bits. If you are adding 16 more bits, then 48 becomes 64 bits. Then that number becomes the interface identifier. But where to add? After 24 bits. Okay, after 24 bits, we have to add 16 bit. In that 16 bit, first 15 bits should be the value 1. The 16th bit should be the value 0. Okay. So F4 to up to this 17. Okay, up to this 17 is 24 bits. So we can take it F4B7, because when you are writing the IPv6 format, a section should contain 4 hexadecimal number. Okay, but this 4 now becomes 6. This 4 becomes 6. Okay, you can refer this. Then 17. Okay. But what to add here? Okay. So 15 once. So 15 once followed by 0. If you are representing this 1111 in hexadecimal number, it is equivalent to F. The next 4 bit is equal to F. The next 4 bit is equal to F. And this is equal to E. You can please check, convert this binary number into the hexadecimal number. So it is equal to FF, FE. Okay. Take these two F and add it with this 70. Okay. So that we have put 4 hexadecimal number in a section. Then take this next FE. And what is the next number? FF. Okay. So this FF I am writing it here. Then as usual 17, 21. Now this number is the interface identifier. And we have derived the interface identifier from the Ethernet address or MAC address. The original MAC address is 48 bit length, but we have derived interface identifier from this 48 bit by adding the number FF, FE and by changing the 7th bit from 0 to 1. So by using these two techniques, two ways we can derive the interface identifier for IPv6 from EUI and MAC address. Thank you.